Electrophilic addition reactions. Alkynes are electron-rich molecules because of the presence of electron cloud around the sigma bond, because of which it can undergo electrophilic addition reactions like alkenes. Here is an example for an electrophilic addition reaction of alkyne. Alkynes are in general less stable and less reactive than alkenes. For an alkyne to be both less stable and less reactive than an alkene, the following two conditions must hold good. The first one is that the transition state that is obtained from the electrophilic addition reaction of an alkyne must be less stable compared to the transition state that is obtained in the electrophilic addition reaction of an alkene. The second thing is that the difference in the stabilities of the transition states of the two electrophilic addition reactions must be greater than the difference in the stabilities of the two reactants, alkene and alkyne. From the reaction coordinate, it is very clear that the transition state that is obtained in the electrophilic addition of the alkyne is closer in energy with respect to the product that is obtained in the reaction. So according to Hammond's postulate, we can think that the structure of the transition state is going to resemble the structure of the product that is obtained in the electrophilic addition of an alkyne. The product that is obtained in the electrophilic addition reaction of an alkyne is either a pi complex or vinylic carbocation. And both of these species are unstable compared to the alkyl carbocation, and therefore the transition state of the electrophilic addition reaction of an alkyne is also unstable. Let us compare the two reactions, the electrophilic addition reaction to an alkene and the electrophilic addition reaction to an alkyne. We know that in an electrophilic addition reaction, the first step of an electrophilic addition reaction is going to involve a carbocation intermediate. In the case of alkene, it's going to form an alkyl cation where the electrons from the double bond is going to make a nucleophilic attack on the hydrogen, and the bond between hydrogen and chlorine is going to leave, resulting in the alkyl carbocation. But in the case of alkyne, it's going to result in the formation of a vinylic carbocation in the first electrophilic addition reaction, where the electrons from the pi bond is going to go make a nucleophilic attack on this hydrogen, thrusting out the Cl-. Here is the relative stabilities of the different carbocations. We know that the tertiary carbocation is more stable compared to the secondary and primary carbocation. But what about the vinylic carbocation? Vinylic carbocations are less stable than the tertiary carbocation. We know that a primary carbocation is too unstable to be formed. But when it comes to the primary vinylic carbocation, it is even more unstable, and therefore the transition state that is obtained in the electrophilic addition reaction of an alkyne is unstable, making the alkyne less reactive towards electrophilic addition reactions. So some chemists think that the intermediate that is obtained in the electrophilic addition reaction of an alkyne is a pi complex rather than the primary vinylic carbocation, which is too unstable to be formed. There is an increased evidence for the formation of pi complex because many of the alkyl addition reactions were found to be stereoselective. So for example, when 2-butene underwent an electrophilic addition reaction with HCl, the two components H and Cl were added in the opposite directions, leading to anti-addition. So only when the intermediate is a pi complex can we get the anti-addition product. And the pi complex was found to be more stable compared to the stability of vinyl carbocation, but it is less stable compared to the alkyl carbocation. Here is the electrophilic addition of an alkyne with HCl. So first, to begin with, the electrons from the triple bond is going to make a nucleophilic attack on this electrophilic hydrogen, and that's going to lead to the formation of a pi complex. So in this pi complex, the hydrogen here is going to be electropositive and the chlorine is going to be electronegative. And in the next step, the Cl- will make a nucleophilic attack on the most substituted carbon, breaking open the ring to form the haloalkene. Alkynes can undergo a second electrophilic addition reaction because the product that is obtained in the first electrophilic addition reaction has got a double bond. So when the second electrophilic addition reaction happens, this nucleophilic double bond is going to go and attack the hydrogen, and the leaving group is going to leave, and it's going to result here, in this case it's going to result in the formation of a geminal dihalide. A geminal dihalide is a compound where the two halogens are going to be on the same carbon. But the second electrophilic addition reaction is going to be slower because we have an electron withdrawing atom here which is going to withdraw the electrons inductively. Now think about the mechanism. What is happening in the electrophilic addition reaction? In order for the electrophilic addition reaction to happen, we need to have a bunch of electrons around it. But if these electrons are pulled by this electronegative atom inductively, then this double bond is not more nucleophilic for the electrophilic addition reaction to happen. So the order of relative reactivities of the alkenes and substituted alkenes and alkyne is going to follow this order, where the alkene is more reactive compared to an alkyne. And then comes the halo-substituted alkene, which is the product that is obtained in the first electrophilic addition reaction of an alkyne. So this also explains why only one equivalent of HCl is used in the reaction, because with a second equivalent of HCl added, the alkyne can undergo a second electrophilic addition reaction. So when you have only one equivalent of HCl, it's going to result in the formation of halo-substituted alkene. But when you have more than one equivalent, when you have two equivalents or excess of HCl, then it's going to lead to the formation of the second electrophilic addition product, which is basically a geminal dihalide when it reacts with HCl. Electrophilic addition reaction to a terminal alkyne is regioselective, which means there is preferential formation of one product. Let's consider this reaction. We have a terminal alkyne. This is a terminal alkyne because the triple bond is present on the terminal carbon. When this undergoes an electrophilic addition reaction with HCl, the hydrogen is going to get added to the carbon, which has the most number of hydrogens. So between these two carbons, which one has got higher number of hydrogens? Obviously, it's going to be this. And therefore, the hydrogen from the protic acid is going to get added to this carbon, leading to the formation of either the vinyl carbocation or the pi complex. Now, once the intermediate is formed, the Cl- is going to go attack the other carbon, leading to the formation of the product. Right? So here, Markovnikov's rule has been followed, where the hydrogen is getting added to the carbon, which has the most number of hydrogens. Now, a second electrophilic addition reaction is also regioselective, where there is again preferential addition of the hydrogen. So now, this can be considered more like an alkene, right? So you have two carbons in here again. When you add the protic acid to this molecule, the hydrogen from the protic acid is going to go to the carbon, which has the most number of hydrogens. So between these two carbons, this is the carbon which has the most number of hydrogens. And therefore, the hydrogen is going to go onto that carbon, okay? And the Cl is going to go get attached to this carbon, leading to the formation of a geminal dihalide, where the halogens are present exactly on the same carbon. An asymmetrical internal alkyne forms two products. Let's see why. Let's consider this reaction. 2-pentane undergoing electrophilic addition reaction with excess of HBr. So in this case, there is a possibility that this alkyne can undergo two electrophilic addition reactions because we are using excess of HBr. So in the first electrophilic addition reaction, it's going to lead to the two products. Here, none of these carbons have got any hydrogens in here, so therefore there is no preferential formation of any particular product. The hydrogen, if the hydrogen is going to go onto this carbon, the Br is going to go to the other carbon, and similarly, if the hydrogen is going to go onto this carbon, the Br is going to go to the other carbon. So there is a possibility that we can get both of these products. So let's write down the two products that will be obtained here. This is one of the products that is formed, and this is the other product that is formed. So both of these compounds can undergo a second electrophilic addition reaction with HBr, to lead to the formation of a geminal dihalide. Now, this is going to have preference. When the second electrophilic addition reaction happens, we have to follow the Markovnikov's rule, where the hydrogen will get added to the carbon which has the most number of hydrogens. So between these two carbons which has the double bond, which one has got higher number of hydrogens? Obviously this one. So the hydrogen from the HBr is going to get added to this carbon, and the Br is going to get added to this carbon. So let's write down the products. Similarly, we are going to do the Markovnikov addition of HBr onto this alkene to get the other product. These two products are obviously different because this one right here is a 2,2-dibromopentane, whereas this one is a 3,3-dibromopentane. In the case of symmetrical internal alkyne, it's going to form only one product because it has exactly the same substituent across the triple bond. So we have an ethyl group here. We also have an ethyl group here. So if the hydrogen is going to get added to this carbon, the two bromines are going to get added to this carbon. And this is the product that you will be getting, right? So which is 3,3-dibromohexane. On the other hand, if you add the two hydrogens here, the two bromines are going to go on to this carbon. This is also 3,3-dibromohexane because for this compound you'll be counting the carbons in this direction. Okay, so this is again 3,3-dibromohexane. So on the whole, a symmetrical internal alkyne, when it undergoes electrophilic addition reaction with HBr, it's going to give us only one product.